let me introduce our first speaker, who is Gillian Wright, and she's a director of the Astronomy Technology Center in the UK, in Edinburgh. And she's also a European PI for the James Webb Telescope, MIRI, so the mid-infrared instrument. And she will give us an update about the James Webb Telescope. So please, Gillian, the floor is now yours.
Thank you. I'm just going to share my slides. Is that working? Oh. What? A minute ago. There we go.
Yes,
we okay?
We see the slides. Yes.
Okay, so thank you for giving me an opportunity to talk to you about the James Webb Space Telescope. So I'm going to talk a little bit about the project and some historical things about it, and the MIRI instrument, because that's where my responsibility has really lain, and then commissioning. And I think you've probably all seen the exciting first images, and I'll just talk a little bit about some of the science with a little bit of an emphasis towards what MIRI's been doing in the last couple of weeks. So in 1997, that was when ESA really started doing early instrument design studies and thinking about what the contributions might be to the James Webb Space Telescope mission. And they formally joined the mission around 1999, and that was when kind of design work really began in earnest. So construction began around several years later, 2003, 2004. And while the project was already into construction before the final conclusion that ESA would definitely provide the Ariane 5 launch was reached in 2005. So mirrors getting made. The MIRI instrument was actually the first one that was delivered to NASA for integration with the telescope. That integration and test process took a long time. It's a big telescope and lots of complicated instruments to integrate. So it wasn't until 2016 that we went into an end-to-end testing of the observatory at cryogenic temperatures, and then launch on Christmas Day. So it was an absolutely perfect launch and a flawless deployment. I think this is still one of my favorite JWST pictures because it was really unexpected that we would see the solar panels deploy before we lost sight of the mission. And it was kind of quite nice to see it drifting off towards L2. Well, not so much drifting off as powering off on a perfect trajectory. So that perfect trajectory on the launch has extended the fuel lifetime of the mission really significantly, which is great news for science. So it has been many years in the making, and some of the challenges have had a lot of publicity along the way. I think it's worth remembering that it is really one of the most ambitious projects that we've done in astronomy and space science to date. It's a huge telescope. It has a 6.5 meter diameter primary mirror. But I think the more challenging thing is the size of the sunshade. And the sunshade's made of mylar. It's incredibly difficult to handle. It has to be tensioned just right. All of it had to be deployed in space. There were a lot of really big engineering challenges that JWST has now broken through and demonstrated how to do. And so the passive cooling is working fantastically well. The entire, so this is the first infrared space mission that has had no cryogenic coolants on board. So there's no running out, warming. It won't warm up because we run out of cryogen. So that sunshade is really doing its job. It's cooled the whole observatory to 40 Kelvin. The telescope had to be deployed and aligned and phased in space. So the whole issue of segmented mirrors, phasing of the segments was a real challenge. The cooler for MIRI, so MIRI is cooled to 7 Kelvin. It brought its own set of technical challenges for the mission to go so much colder and achieve the mid-infrared performance. The cooler is not one of the worries with closed cycle coolers is that they're fridges, and there are pumps, and pumps, as we all know, vibrate. But actually, it again is being demonstrated now to be properly vibration-free in flight. And the instrument capabilities comes with a full suite of instruments, more akin to what you would normally see on a large ground-based telescope in terms of their complexity and the scope of the different observing modes that they support. So the European role has been the launcher, obviously, the NIRSpec and the MIRI instruments. MIRI, I'll say a little bit more about MIRI in a minute. It actually isn't a purely European instrument. It was a European-US collaboration that was needed in order to get that fourth mission instrument, especially with all the technical complexities of different detectors needing to be much colder. And ESA are now part of the STSCI Operations Center for the mission. So what really strikes me about this slide of who's all involved is the number of companies from around Europe is almost comparable to the number from the US that have been involved in different parts of building the mission. So it is truly a big international collaboration between the US, Europe, and Canada. MIRI, the mid-infrared instrument, was in the end agreed that it would be a 50-50 partnership between Europe and the USA that would provide that. So I am the European PI for MIRI. In the US, that would be George Reiki. And we've worked together to make MIRI happen. And in Europe, MIRI was done in what I think is fairly classic collaborative consortium way, as through additional members state contributions. So each country funded their own contribution to MIRI. The UK led, and then that was half of the MIRI instrument. JPL provided the detector systems and the cryocooler, and we focused on the optics and the performance of the instrument in Europe and building it here. So MIRI is a little bit unique amongst the JWST instruments because there were only really the resources to put one mid-infrared instrument on the mission. We provide spectroscopy and imaging and coronagraphs, and we've got more than one spectroscopy mode all built into MIRI. But this slide's a nice summary of the sophistication of the instrument suite that's provided. Different techniques, aperture masking, as well as coronography, for example, for looking at planetary systems, wide field and sensitive imaging, more than one way of doing that, more than one way of doing near-infrared spectroscopy of faint galaxies, and then MIRI bringing the mid-infrared science. So we've had to commission all of that. There has been 6 intensely busy months. The first half of the commissioning period since launch was really taken with aligning the telescope and commissioning the telescope optics and cooling MIRI down. It took us a long time to get cold because we had to wait for the observatory to get to 40 Kelvin and then turn on our cooler. There was a lot of cryogenic instruments you need to take an awful lot of care around ice, for example, not getting ice on your optics. So the whole cool down is quite a difficult thing to control. It all went perfectly well. And then for the last 2 months, May and June, we're just incredibly busy with the first commissioning data coming in. And that was very exciting as well to see all the data, but it has been a very busy period to get everything working as well as it is. And this, you will have seen this image probably in the press releases from NASA. You may have done, showing the alignment of JWST. It also shows how JWST can take data in the instruments share the field of view of the telescope. And what that means is that you can observe with the instruments all in parallel. And this is a field in the Large Magellanic Clouds that we used for astrometry, but it is actually showing you the correct view of how JWST, with all its instruments turned on at the same time, would take images of the Magellanic Clouds. And if you look closely at it and you look at the MIRI image, you can see the dust emission in the MIRI image, and you can actually trace that dust lane all the way across with your eye to the dark stripes that you see in the NIRCam and the nearest instruments where the dust is blotting out the starlight. But with MIRI, you're seeing the stars through the dust, and you're seeing the emission from the warm dust itself. So this is the sharpest image of a star that's ever been made. The large ground-based telescopes can't do this because even with adaptive optics, they are still somewhat limited by the atmosphere. I think it's showing you what happens when you have a hexagonal mirror, but that's fine. We knew about that. There are little galaxies everywhere in this image, and that was part of the story of commissioning. I think we were finding little galaxies everywhere, sometimes in places that we didn't really want them because we were trying to measure accurate point spread functions, and little galaxies would pop out. And I think there's a paper now on Archive from the one of the commissioning teams with us where they really serendipitously discovered a new galaxy. So it's the observatory is working extremely well. There are some stray light features that were unexpected in all the instruments. There are many things that are working far better than expected. There's detailed information gone out to the community about the performance. It's also on Archive if you want to go and look at it in a little bit more detail. This MIRI is really proving that it's doing what we said. This was one of the first comparisons that was put together of what a change having a mid-infrared capability on a big telescope like JWST in space makes in terms of both the sensitivity and the spatial resolution. So it's comparing previous mid-infrared data in Magellanic Clouds with what MIRI can see. And it's probably about my favorite image. So it is a huge leap in capability, and it very rarely happens this big a change is made in the history of astronomy. So although I'm going to talk about science and some of the science we expect to do, I think the thing that's going to be really exciting with JWST is the science that we don't anticipate and the new discoveries. So the leap in sensitivity, and in MIRI's case, combining that with the massive improvement in image sharpness and spatial resolution, it is the equivalent of if we had Galileo's telescope and then we suddenly had the VLT in terms of the change and the scale of the step, and we didn't have any of the half-meter size telescopes and 1 meter telescopes and all the rest of them that have been built along the way over the last years and years and years of building up astronomy knowledge. So I think, you know, it's a huge leap in capability that has been made, and I think it will do transformative science for that reason. So the capabilities of the instruments, they all have a very big dynamic range, so we can observe bright things from the solar system all the way out to very faint first galaxies, and the instrument suite was designed to put together a mix of capabilities so that when the creativity of the worldwide astronomical community gets going on what science they want to do, the instruments are there to enable that with many different modes, many different ways of doing spectroscopy or imaging. And I'm just going to talk about a couple of examples that I think are going to be particularly important and in the first year of science operations. But before I do that, it's interesting to look, in fact, at this is the type. So the blue on this chart is applications in different areas of science. And then the red is what the peer review panels actually awarded in terms of time to use the telescope. And you can see that it really is spread throughout the questions in modern astronomy, from our solar system, star formation, stellar death, how galaxies form and evolve, and of course exoplanets. So it's a very broad range of science that will be done in the first year of operation. The other thing that is interesting about it is the importance of spectroscopy. And so if you instead of breaking it down by science area, you look at the telescope time that's been awarded for the first year of operations in terms of what techniques are being used. 70% of it is different spectroscopy techniques. And I think that is quite interesting. So thinking of spectroscopy techniques, one area of science that was a very big bar booming through in that was exoplanet studies. And the reason for that is I think it's really going to open up a new era in doing exoplanet transit spectroscopy and starting to actually study the exoplanets and understand the chemistry of what is and isn't happening in their atmospheres. So this is a simulated spectrum of the exoplanet that is getting the most attention during cycle 1 of JWST time. It's a sub-Neptune type planet. There's about 80 hours of time invested in this. So this is a simulation of what at the end of that the transit spectrum may look like. The reason so much time is being expended on it is because it's known from some Hubble data that there is something that is probably a water vapor absorption feature in the spectrum, but they have only a very, very small piece of spectrum around 2 microns, and the water lines are, unless you have a much bigger spectral range, the water lines are degenerate with things like methane. But because there's a putative detection of water in this planetary system, there's a lot of time going to be invested in studying it properly. It's not the only exoplanet atmosphere that will be getting looked at, but it's certainly one. So this was the NASA image that was released of the first JWST exoplanet transit spectrum. So the way these spectra are done is what you're doing is you're measuring the transit depth as a function of wavelength with a dispersing element, obviously in your instrument. For MIRI, we have a mode, a low resolution spectroscopy mode that's implemented with a prism in our filter wheel that's designed to do this kind of science. And we also have some data, although wasn't in the first release. This is some commissioning data. So this is actually the first MIRI transit. It's of a super Earth called L1689b. It's about 4 Earth masses. We chose it during commissioning because it's a very challenging object to do. That transit depth is about 500 parts per million, so it's very small. And it was very straightforward to do. This data has not, one of the things that I think is a real transformation with JWST in its capabilities is that it is making some things that people have had to work very hard to get the data and to get the data right, much more straightforward. You can see in the top of this graph, the transit depth is already visible just in the raw data. So we haven't, you know, there's been, there's a slight, very slow, the detectors on JWST are very stable, which is one of the things that is difficult about doing this kind of science with Hubble and with Spitzer, is drifts in the detectors, and you can see in the MIRI data, there's almost no drift, and very straightforward to take it out and then fit to the planet. Like I say, that's about 500 parts per million. We've demonstrated from the residuals that we should be able to get down to 50 parts per million transits with MIRI during cycle 1 observations, which is, you know, is a real demonstration of the power JWST has for this kind of science. So kind of moving much further away, the other very large fraction of JWST time that you saw in that graph is in the study of how galaxies form and evolve. So how star formation changes galaxies, how stellar mass builds up, and how the whole chemical enrichment of the universe, what the metallicities of the galaxies are and how they change with time. And there's a lot of time awarded in the cycle 1 programs to look at this and to really push back to the epoch of reionization and the first galaxies and stars that formed. And so this is the deep field that was released. There are many papers on arXiv this week, a lot of excitement about this data and some of the early release science programs that are ongoing. You know, number densities of galaxies seems to be much higher than expected at redshifts. There are claims of papers in papers of, you know, more than one galaxy 5 sigma at redshifts in the 13 to 20 range. Definitely enough, I think, to be saying there are discrepancies with models. I would point out that the papers, of course, have not been peer reviewed yet. And also that this is not yet very deep data. So the data that this is going to, the depth of the images that are being analysed currently, they're going to about 29 magnitude, so they are going deeper than Hubble. But the plan with the cycle 1 observing time is to get 2 magnitudes deeper than that still on the same region of sky as the Hubble deep field. So I think there's a lot of excitement coming there. And nearby galaxies, this is my favorite MIRI image. So on the left, you have the Hubble image of Stephan's quintet. On the right, you have the MIRI image, and I think it just so demonstrates the difference it makes to be able to look at galaxies in the mid-infrared. What you're seeing here is the streamers of star formation. And the active nucleus in the top right galaxy was known about from X-ray data. It's a Seyfert-2 galaxy, so it is heavily obscured. And as you can see in the mid-infrared, moving to the longer wavelengths, there's a diffraction limited point source image in the middle of that galaxy. So when we're really seeing in the MIRI image the star formation in the tidal tails created by the interaction between the galaxies. And to follow that up, we have MIRI spectroscopy. This is done with our integral field unit. Integral field unit spectroscopy is still relatively new. It's certainly never been done in the mid-infrared before. So what you are able to do using image slicers is to take simultaneously spectrum and image at each wavelength within that spectrum. So what's shown here is the reconstructed image from the MIRI image slicers of the active nucleus in the Stephan's quintet galaxy. And then you can take within that image is a data cube. So because you can then extract spectra for any point in that image. What's illustrated here is the big difference between, so if you're looking immediately in the region of the active nucleus, what you're seeing is the dense obscuration here around it. So you're seeing the silicate dust, the dense molecular hydrogen lines of the obscuration around the nucleus. If you look a little bit off nucleus, where there's some evidence in the X-ray for a jet, what you're seeing is the ionized gas that's being heated by the active nucleus. We know that this, so the neon lines that have been detected in this mid-infrared spectrum, the excitation of those neon lines is high enough that it's not stellar radiation. So this is not star formation that we're seeing here. This is actually the AGN heating the medium in the nucleus of the galaxy. So I think, again, is pointing to the exciting science that we're going to see coming in the coming year and future years from JWST. So if I was to summarize it, I would say the performance is exceeding expectations. The spatial spectral resolutions and the sensitivities have already been shown in the commissioning data and the early release observations to be transformative. It is going to provide a new view of the universe, and astronomy is an observational science. So, you know, when we go and look, that's when we discover new things, and it's ready to go. So I would like to say a big thank you to the MIRI commissioning team. They're responsible for having taken most of the data, the MIRI data I've shown you today, and also Roberta Maialino and Sarah Kendrew generously shared some of their slides. They've been giving similar overview talks in the last couple of weeks. So thank you, everybody.
Thank you so much, Gillian, for a nice talk, and we are all awaiting the amazing science that James Webb will deliver. So let's take questions now. We have already a few in Q&A box, but I encourage everybody to continue submitting questions. We have several minutes for this. So the first one comes from Alexander, and he asks, GWST has this very distinct 6-edge star PSF. Why is that not removed in the images?
I think it could be removed in the images, and in fact, if you look in Hubble images, they usually clean diffraction spikes out. In fact, because JWST is truly a diffraction limited telescope at all the wavelengths it's used at, the diffraction pattern changes as a function of wavelength, and so it will take some time to develop the algorithms as a function of wavelength to take the diffraction pattern out, but I'm sure we will start seeing images without it. And I think it's very pretty. And if you're looking at your data, you know, yeah, sure, you take the diffraction spikes out, but you better know you took a diffraction spike out if you're looking at a faint galaxy behind it.
I agree, artistically it looks very pretty indeed. So the next question is from Heis, and he asks that you said that the near perfect lunch results in a longer science time, and do we already know roughly how much more time is that?
From the point of view of fuel, the spacecraft fuel should last for at least 20 years, which is roughly double what was expected, or double what had been planned for. So the lifetime really, I think, will be limited in the same way it has been for Hubble in terms of what the lifetime of other parts of the mission are. You know.
Thank you. The next question comes from YouTube, from Simon. He first of all says that your talk was great. So
thank you.
And he's curious about what data policy you have, and will raw data be released, and is there an embargo?
So the raw data is released. There are two types of JWST program. There are some programs called Early Release Science and Director's Discretionary Time. And for those, the raw data is made public instantly. Well, within a few hours. By the time it comes to the ground, it's processed through the pipeline and then is made available. So within hours of it, everybody gets the data at the same time. And then the guaranteed time observations of the instrument teams and the programs that have been competitively awarded time, they have the raw data has a proprietary period of 1 year. And then it's all public.
So I don't see any more questions, but we have some time. So let me also ask a personal question. So you participated and designed the MIRI instrument, and I'm wondering what was, your personal scientific question that you wanted to address with that instrument?
Star formation in relatively nearby galaxies. So galaxies around from the current epoch to redshifts around 2, where there's a lot of star formation, and what the feedback is between when you have an active nucleus, what the feedback is between the interaction, which you can't really see without looking in the mid-infrared to understand how much of the luminosity of those galaxies is coming from the star formation and from the active nucleus. And I think that's still one of the things that interests me, but MIRI was designed to do a lot of other science, and I'm excited about all of it.
Sure. Okay, so we have another question. From Sasha. I would imagine that the amount of data is quite large. Is the downlink limiting the amount of data you get, or did you get around that with the onboard process? And very great talk as well.
There's very little onboard processing of the data. It's all coming down to the ground, pretty much.
Okay. We still have some time if you guys have question. Yes, Jean-Baptiste asks, are the data continuously downloaded to Earth?
No, there's contact. I think it's once, I'm not sure if it's once every 24 hours or once every 12 hours. And during commissioning, there was more contact than there will be in normal operations. So I'm personally a little bit confused by that, but I think it's once every 24 hours.
Okay.
Valeriya, may I ask a question?
Sure.
I had a question about, well, firstly, Gillian, thank you. That was a wonderful talk. And a question about MIRI and the other instruments, the image you showed about them all in the same field, and you mentioned how they had all been used in parallel. Is that commonplace for them all to be used on the same field, or is that a special occasions type thing? When I saw the slide about how you'd shown the project time for the different instruments, looked like the MIRI coronagraph was limited, and I can see how that wouldn't be used commonly, but will it be common for both the NIRCam and such like to all be used at the same time?
So one mode that is commonly, so the graph showed you what we call the prime instrument. So when you write your telescope proposal, you say, I want to do MIRI imaging of this, and then I'm going to turn the NIRCam on at the same time. So the deep imaging, an awful lot of those programs are using both MIRI and NIRCam in parallel, and then because they look at neighboring areas of the sky, you have to think about how you plan out your mapping if you want to have simultaneous near and mid-infrared data on the same source. But in general, the deep field imaging is being done by using the instruments in parallel. And with MIRI, we're using our imaging capability sits in parallel to our integral field spectrograph. So a lot of our programs are, even where we're doing integral field spectroscopy of faint high redshift galaxies, we've also got the MIRI imager turned on, and in some cases NIRCam imaging as well, doing deep fields in parallel. So that kind of parallel observing is going to get used a lot.
Thank you. There's some other questions flooding in now.
Yes. So one other question from Jean-Baptiste. What do you think are going to be the first big and exciting new result that will be published in the coming months?
I think it will be something like methane in an exoplanet atmosphere. That would be my guess. Although I would have to say that the extragalactic community are being very, very busy at the moment analyzing those deep field images.
Thank you. And let's take one last question from Martin, who also says, fantastic talk. Can I ask about the typical cadence for detectors discretionary time observations? How quickly and easy will it be possible to deploy the telescope to observe aurical sky location? Not so relevant for LISA perhaps, but important for example, follow-ups for binary neutron stars direction by ground-based gravitational wave detectors.
Yeah, so there is I think so there is a way that you can request a target. We call it a target of opportunity for that sort of thing, and there is time held back in the planning of the cycle to enable that to happen. So you can put in a target of opportunity request at any time during the semester, and they'll look at it and see how quickly they can respond. But the director's discretionary time, there's a call out every year that happens partway through the observing cycle. So there's one just gone out now, for example, which can be, you know, that something that you only need a very small amount of time, not necessarily something like a transient, but something somebody's thought of after seeing how the observatory is working, for example. I think would be considered for that. Although I would have to say that I have no responsibility for policies. They sit with the Space Telescope Science Institute.
Sure. Okay, so I think we exhausted all the questions. So let me thank you again for an excellent talk and very clear, exhaustive answers on behalf of everyone.